Hey everyone, so this is the second video on the kinetic theory of gases topic. This one's going to be a little bit shorter than the other one. There's really not as many questions and more a little bit more just talking about concepts. Like I said, we're going to talk a little bit more about some of the other properties that we can discuss and how it relates to this kinetic theory of gases, the fact that gases are made up of small little particles that are moving and so on and so on. So for example, we could talk about phase changes and how phase changes are actually related to this concept. So like I said, the PV equals nRT, the ideal gas law, that is a good approximation for gases, but it doesn't really work too well as we get closer and closer to things like the phase change or low pressures. Now, this graph kind of is supposed to show that idea. So here, this dotted line is supposed to represent the ideal gas law, and the solid lines are representing like what's actually going on. So as we can see here, when the pressure is fairly low and when the volume is fairly high, so what that's usually referring to is the fact that the molecules aren't really that close together. Things like A works really, really well until it starts to get a little too close, and then you'll start to notice that there's does start to be a little deviation between what we expect from the ideal gas law and what we actually end up getting. When we look at something like B, so at a slightly lower temperature, we'll see that it does follow the trend, but then all of a sudden, again, once it starts getting a little too close, we'll start to see a little bit of a shift between what we expect and what we actually see. And then things like C and D, where we actually get really, really close to the phase change, here being right before there actually does end up being a phase shift. And then over here, where there actually is a phase shift in the middle, we do see that it just kind of completely deviates from what we would expect to be this nice inverse curve. Um, Now this makes sense because, as we said, uh, the ideal gas law is pretty much assuming that there is no interaction between particles. But as we decrease the volume and we start increasing the pressure, the molecules will start to interact more and more. So the reason why these start to deviate is because all of a sudden at this moment, uh, for this temperature, there starts to become more interactions between the particles that we no longer are assuming occur. Same thing here. There's interactions that we're not taking into consideration. Um, and during these phase changes, what ends up happening is that there actually does end up being significant amounts of intermolecular forces that we no longer can ignore. So that's why it ends up being shifted like this, because with gases, we're assuming that the particles aren't really connected, because that's like the whole thing. Each molecule is free and unfettered from each other. But once it starts getting close to these phase changes, well, all of a sudden now the molecules are starting to link up together. And when it does start to become uh, going into the liquid phase, it will start to actually um, connect with each other and actually interact and link up. Now, there's a special point called a critical point, this point right here, that basically it's the idea that we'll mention this, but it's kind of the difference between a gas and a vapor. So we can actually make these types of graphs called pressure and temperature. Now you'll notice there's two different graphs. I'll mention the difference later on, but one of the things that these graphs tell are their phase graphs. So for example, we kind of saw this in one of the previous videos, but you could see how at a certain pressure and at a certain temperature, we can go from something like a solid, a liquid, and a gas. Now, any temperature below this critical temperature will end up making it so that the substance, when it goes into its gaseous phase, will actually be a vapor. Anything above the critical point, and we end up getting a gas. So there actually technically is a difference between a gas and a vapor. Um, so this actually says right here, at the temperatures less than the critical temperature, a gas can change into a liquid if enough pressure is applied to it. But um, if it's higher than the critical point, then there's no way that we can actually go from gas to liquid. So that's actually, we can see it here, like the critical points at this location. This white section here is it being in its gas phase. So enough pressure and it'll go into a liquid. But over here, when we start getting above it, adding pressure or decreasing pressure, and it's just going to remain in its gas phase the entire time. Um, then yeah, so these are called phase diagrams. They're pretty important to be able to use. This is what I was saying before, that uh, below the critical temperature, the gaseous state is called a vapor. And what that's usually referring to is that it's capable of changing between either into a liquid or a solid. Anything above it is what we would normally consider a gas. So there actually is technically a difference between a gas and um, a vapor. All right. Yeah. So this is just talking about the PV curve. Okay. So I want to refer back to this. So you'll notice that this line that's between the solid and the liquid looks different on these two diagrams. Mainly, this is referring to the fact that this up here is actually water, and this is referring to the fact that solids tend to have a lower density than liquids. So this is kind of the whole idea that they expand when it freezes, and that's, we can see it in the curve here as opposed to something like this. These are some critical temperatures over here and the critical pressures that kind of relate to it. All right, so there is one special substance. It's called a supercritical fluid. Basically, what ends up happening is the temperature and the pressure is ends up being above this critical point. And what ends up happening is that we end up not getting a distinct liquid or gas phase. It kind of just all looks the same. So if we look here, this is supposed to be a typical graph. You know, we have the solid phase, we have the liquid phase. It's a little bit more broken up. So for example, we see the gaseous phase right here above the critical temperature. We have the vapor phase below the critical temperature. And then we have this point, which is called the liquid phase and the compressible liquid phase. And then this is where we get the supercritical fluid. So it has a high enough temperature and a high enough pressure. Um, and this actually ends up being a really interesting thing. Um, so we end up seeing that small changes in pressure and temperature result in large changes in density. Um, you will most likely work on this if you take continuing physics in Stony Brook. When you get to this senior lab, they have stuff where you kind of work with helium and you end up making, you know, supercritical fluid helium, where a lot of unique things end up happening. Um, yeah. Oh, so this is going to play a part in, I believe, the next lecture, the concept of heat. So heat, as we said, is the energy that gets transferred from one substance to another, that is caused by temperature differences. Now, one thing that's going to end up being super important is that heat can do one of two things at a time. It can either result in the temperature changing or the phase changing. And when it's changing its phase, the temperature does not change at all. So it can do only one of the two things. Now, we can also talk about evaporation using this whole kinetic theory. Now, the idea is that, like, if we consider a liquid, so we have a liquid and the molecules are linked up and they're all moving around. Now, at the surface level, we do end up having some molecules that will end up having enough velocity that they'll be able to break away from their inner molecular forces and then leave the liquid. Um, we can use the Maxwell distribution to see how many molecules can actually break away uh, based off of the temperature, how that relates to the kinetic energy, and then what speed is necessary to break those bonds. Now, one important thing is that when the atoms kind of leave, there are also going to be some atoms up here that are moving slow enough, or some molecules, sorry, that are going to be moving slow enough that when they collide with the surface of the liquid, they'll also be captured. So there ends up being both things happening. You end up having some evaporation where the molecules in the liquid are breaking away from their bonds, and you also will have some condensation, basically the molecules coming from the gases, the vapor, and colliding and being captured by the liquid. Um, Now, if the numbers are equal, so if the number of molecules that are leaving the liquid that are evaporating is equal to the number of molecules that are condensating, uh, then it's in equilibrium, and we end up calling that a saturated vapor pressure. Basically, meaning that the gas up here is no longer able to take any more gas, that it's kind of any more molecules, that for every molecule that evaporates, they have to have like another one almost condensate. Um, Now, over here is a list of the saturated vapor pressure related to temperature. So, for example, if we have a temperature of 20 degrees Celsius, well, that means that we can only have a vapor pressure of water saturated vapor pressure of 17.5 torr. Now, this just kind of says that the vapor pressure of a liquid ends up increasing as we increase temperature. And then, um, yeah, so here we go. Air, so as you know, air could be dry or humid. What this is actually referring to is the amount of water vapor that's actually in the air. Um, so when we talk about humidity, the way we actually get it is we're going to take how much actual pressure, how much water is actually in the air, and we're going to divide it by how much water can be held in the air. So if we have a case where uh, we can only have, like in the previous case at 20 degrees Celsius, we can only have 17 and a half torr of water pressure in the air. If we have that, then that means if we actually have 17 and a half, then that means our relative humidity ends up being 100%. So when we say that air is dry, what that's usually referring to is the fact that the amount of air pressure or water pressure actually in the air is significantly less compared to how much could be held in the air. And yeah, this is the whole idea is that humidity, when it actually reaches 100%, it's no longer able to hold any more water, and there's no longer any more evaporation going on, or at least no net evaporation. Like I said, you'll end up getting, you might have some water vapor actually evaporating, but an equal amount is also condensing. Now, this actually is one of the reasons why it always ends up feeling hotter when it's humid. If you've ever talked to someone who's in the not Midwest, yeah, Midwest, Southwest, like in Arizona or Texas, you might hear them say things like, "Oh, but it's a dry heat," referring to how, something like 120 degrees isn't really that hot to them. It actually does have a lot of importance because there's a few things going on. First, when you are in a dry heat, anytime your body starts to sweat, you will end up getting a lot of evaporation going on. So your body, when you start sweating and that sweat evaporates, does cool your body down a bit. Unlike being somewhere like here on Long Island, where since we're so close to the water, we tend to have very humid atmosphere. When we do get very high humidity, we end up getting cases where your body cannot evaporate your sweat, so the sweat just kind of builds up, never actually evaporating and never actually cooling you down. So yeah, sweat no longer ends up cooling you down. Now there actually is a second reason why dry heats tend not to be as intense as humid heats, and that's also because of the fact that the air in the atmosphere is also kind of carrying the heat over to other places. So, for example, in if we go back to Arizona and Texas, you've probably heard of cases where it could be over 100 degrees during the day, but then once the sun sets and once it becomes night, all of a sudden that temperature drops to something like 60 degrees. Um, that usually happens because of the fact that because the air is so dry, it's not able to contain the heat as well. So once the sun's gone, the heat also goes. It's also one of the reasons why a lot of times in those areas, you can actually cool down just by going into like underneath a shade or just going into a house and not really needing an AC unit. But go to some place like Florida or Long Island and you can't get away from the heat. You can go indoors, but because of the humidity of the air, all of a sudden that heat is still transferred into the inside. Or when the sun goes down, it does get cooler, but it's not significantly cooler. So a lot of this humidity does actually play a part as to why heats feel differently depending on where you are. All right, so I think this is pretty much one of the only questions in the topic. But you can pause the video, work on this yourself, and we'll go over it in a second. All right, so we want to know what the humidity is. Now, we're going to use our equation. They said it's 30 degrees Celsius, so here's 30 degrees. The most amount of pressure that the air can withstand is 31.8 torr. It says that we currently have 21 torr. So what we're going to do is take the 21 divided by 31.8 times it by 100, and we get that the relative humidity is 66%. Now, a little bit more about this whole partial pressure and water pressure stuff. So, um, where is it? Okay, so here it's saying that there are actual times where the partial pressure of the water in the atmosphere will actually exceed the saturated vapor pressure. And when this happens, we end up getting what's called a supersaturated setup. Now, when this occurs, this doesn't occur normally, like in the sense that, you know, as I said before, if the temperature is 20 degrees and it can only withstand 17 torrs of water, it can only take that amount. However, when you end up having a drastic temperature fluctuation, so if the air is currently holding, a certain amount of water vapor in the air, so it's has a relative humidity that's high but less than 100%. If that temperature all of a sudden drops about 10 degrees or so, then all of a sudden the water that's still in the air is still being held, but now with the drop in temperature, it can't hold the water anymore. And this ends up resulting in excess water needing to be condensed. And usually this occurs in the form of dew, fog, or rain. So that's what's going on when you end up getting this, is that you end up getting a situation where it was really hot at one point, a lot of water vapor was in the air, it got very saturated, but then all of a sudden the temperature drastically dropped, resulting in the water vapor becoming or the air becoming supersaturated and then needing to condense that excess liquid, depending on how much it was holding at the time, and the difference, it could condense in a little bit as dew, or it could go as extreme as in rain. And we usually call this a dew point, basically what temperature needs to be at in order for it to become saturated. So, for example, it kind of goes back to this. So if they said that 21 torr was how much water is in the air, we can figure out what the dew point is by looking up here and see where would this become saturated vapor pressure. And if we're looking at this, it's going to be somewhere between 20 degrees Celsius and 25 degrees Celsius. More likely to be something like 23, 24 would be the dew point of this air pressure. So for this question, you have that the relative humidity is 66% and that the dew point is about 24 degrees, 23 degrees Celsius. All right, so this is just a little bit quick comment about the van der Waals equation. So I had mentioned before about the whole ideal gas law. It's good, it's a good approximation, but we have this other one called the van der Waals equation, which does actually take into account some of the things that were ignored in the ideal gas law. Things like the fact that the particles do have a finite size and they will interact with each other during certain volumes. Now, this is an improvement and does work a lot better. However, it's still not perfect. So this kind of shows the idea that, like, I guess this dotted line is being used to refer to the what's actually going on, but then the solid line is what we would normally expect using the van der Waals. Like, you can see it dipping in a weird way. So it does get closer to what we expect, but not perfect. All right, so like one example, we said before that assuming the molecules have a finite size, well, we know that the molecules must be at least a distance 2r apart. That it's impossible for them to get any closer than that. So we can actually say that of the given volume, there is a certain volume that is unavailable, and we're going to represent that with a B to say that volume is not possible. So what we do is we call that NB for the number of moles times the amount of volume that's not possible per mole. Now this one, that's easy at least to find. We could just figure out how many molecules are in there and the size of each molecule. And then we also have to take into account this whole the forces between the molecules. So this is related to pressure. We end up getting this altered equation that looks something like this. Not going to go into full detail with this, but the whole thing is that A and B end up known for the gas, but we can only know it through measuring rather than calculating. It's not something that we can figure out. We just kind of have to do it almost through a lab situation where we set it to some pressure and volume that the ideal gas law doesn't really work at, and then use this equation to figure out what A and B is most likely equal to. There's another thing that you're not really going to talk too much about, but it's something called the mean free path. Basically, it's the idea of how molecules will actually move in related to how often they collide. So this is the average distance a molecule travels before it collides with another molecule, and that's what we call the mean free path. So typically, if there's more molecules, if the volume is small enough, you'll end up getting this mean free path to be very, very small, as opposed to if your volume is really big and you don't really have much going on in there, where the mean free path would get a lot bigger. So this is kind of saying that it's inversely proportional to the radius and the concentration of the molecules. So that kind of goes back to what we're saying, that, like, the more molecules they have, or the smaller the setup, the smaller this mean free path will be. So the typical mean free path for air molecules, so at STP, this is the number of molecules in a mole, and this is the volume of a mole. So our concentration will end up being this. if we plug in these numbers, and this is just some typical air molecule, we end up getting that it ends up being about 300 times the diameter of the particles. So what that's usually referring to is that the particles will travel about 300 times their size before they hit into another particle. So that's really all what the mean free path is referring to. It actually, though, has a much bigger um, importance with something like circuitry. It has something very similar with that, where you can talk about the path that the electrons travel. Another thing that we can talk about and how it relates to kinetic theory is the concept of diffusion. So diffusion is the idea that um, if you have two substances and there's a difference in concentration, that that things will start to move from the high concentration to the low concentration until you get uniform concentration. So, for example, if you have water and you drip a little bit of food dye here, it will spread out and diffuse around until it's spread out evenly. Um, the whole idea is that you're not really going to get a situation where there's all these molecules in one area and not much going on somewhere else. And again, we can think of this through the kinetic concepts because particles will want to move freely where they are. So, like a particle here that's moving to the right isn't going to bounce back until it hits something. So, particles that move to right will continue moving to the right until they hit this boundary here. And the particles moving to the left are going to continue moving over here until they hit this boundary here. And then the particles that are colliding over here will actually bounce over into the other areas. So, um, yeah, so that's kind of the whole what's going on at the microscopic level for diffusion. This ends up becoming, we have an equation called Fick's law, which just talks about how quickly it diffuses and stuff. All right, so these were the two main things that we talked about. We talked about the average kinetic energy and the RMS speed, as well as kind of how we graph, how the graphs end up looking. And we also talked about relative humidity and how we'd figure that out, as well as dew point stuff. Okay, chapter 18, the problems are going to be due Monday, and these are the questions. Uh, that's about it. If you want, you can actually stay a little bit longer as we go on to the one extra question that I have at the end. All right, so here's the extra problem that I have. So you can pause the video and work on this yourself, and we'll go over in a second. All right, so we want to find the RMS speed of an amino acid that has a molecular mass of this at a temperature of 37 degrees. And then we also want to do the protein molecular mass that has this at this speed. So at this temperature, sorry. So first thing that we have to do is figure out what the actual kilogram mass is. Then we use the RMS velocity equation, plugging in the Kelvin of the temperature, and we end up getting that the RMS speed's 294 meters per second for the amino acid. And then for part B, for the protein mass, we just have to increase that, change that mass. Nothing else really changes. And we end up getting 9.54 meters per second for its RMS speed. All right, that's about it. If you have any questions, please let me know. Otherwise, I'll see you later.